what I'm going to talk to you today about is the application of arc flash analysis as it applies to primarily data centers. What I'm going to go over, and I understand I have an hour, hour and a half to go through this, right? Yes, okay. Okay. So what I'm going to do is at a very high level, because at 20 minutes, I really couldn't put together a case study, but what I wanted to do was I wanted to talk to you about some of the general considerations we all basically are going through when we're doing arc flash analysis, some of the key aspects of this and how they may or may not, sort of affect what you do for a data center environment. I want to take a look at how our approach has been changing to arc flash analysis and labeling as a part of the process, because this is a dynamic thing. When I first started in this business, we used to do our coordination studies using, paper and French curves and over a light table, right? So things have changed quite a bit. But our understanding of arc flash, how we apply and more importantly, how safety considerations are taken into account, evolves over time, and our approach to it is evolving as well. So, we've been talking about putting aside out a star for a second. We know that coordination, selective coordination studies, has always been a combination of an art and a science, right? It always has inherent in it some trade-offs. Typical trade-offs are going to be, the things like if you're trying to get more selectivity, that generally means that your protection is not going to be as good. Generally speaking, if you're trying to get more protection built into it, you're going to have to sacrifice selectivity to a certain event. Well, when it comes to a data center environment or mission critical environment, the most important aspect of a data center, as anybody that operates, designs, or has met a data center operator, is it can't go down. We talk about reliability is number one in a data center. And so selectivity is the natural sort of inherent approach that most data center operators and owners are going to want you to go towards. They're going to basically say, you know what, do whatever you do, I don't really care, I just can't go down, right? So they're going to want to prioritize selectivity. Problem with that is, as you know, is that, or the challenge more likely, is that as you try to improve selectivity, what you're going to do is you're going to introduce time typically, putting aside some other sort of different approaches. If you're doing a conventional distribution system, what you're doing is as you're increasing selectivity, you're necessarily increasing operating time. And as you increase operating time, you know what you're doing to the incident energy, right? Because it's a square function, it's going to just basically make the incident energies that much worse. So that's kind of what you're up against. The other part of this is that if you look at it, is that almost everything you do in a data center, because they're so averse to taking a data center down, even though we design our data centers with reliability and redundancy built in, even a tier 3, tier 4 data center is concurrently maintainable, it's fault tolerant, all these sort of aspects, which theoretically means that you'll basically be able to do anything you want to the data center and essentially do some of these operations without being energized, so inherently safe environment, right? The problem is two things. One is even with those sort of design features built into a data center, most data center operators it'll be like pulling teeth to get them to do anything to take the load down. It's just basically not something that's inherent in their nature. Depending on the type of client, if it's an enterprise client and it's their own data center, you might be able to work with them to a certain extent to do some maintenance outages, do some other things with them, but most clients are, if they're especially a colo provider or they're basically relying on uptime for their revenue generation in general, because they're providing that managed service or something else, getting it downtime is incredibly difficult. Putting that aside, the question becomes, is even if you decided that you were going to do a maintenance activity and you were going to put your system or a portion of your system into a maintenance mode, the switching operations that are required to do that are typically going to be done in a live environment. So this comes up to another aspect of this that's been really sort of puzzling to me. We've been talking about arc flash, doing arc flash analysis for years now, better than a decade probably. I don't know. How long have we been talking about this? It is still one of the least understood, from an operator, owner, and even some other designers, least understood with the most misconceptions sort of aspect of the electrical engineering or the power system analysis that we do. I mean, most everybody up to this point has got a fairly good understanding of short circuit analysis. Some of them have a little bit better understanding of coordination studies. But when it comes to arc flash, we're still dealing with a lot of people who have some misconceptions. And one of the things that, for instance, that I have to deal with is I do an analysis, I send it out, I have the labels and everything else come up, and a couple of days later I'll get a phone call, and the operator will go, does this mean I have to put on my PPE for blast suit, the Michelin suit as I like to refer to, the Michelin man suit, when I'm putting my UPS into bypass? Well, technically, no. If you read the NFPA 70E, there's a fine print note, which they don't call fine print notes anymore. It's informational note. It's going to take me a while to adjust to that language change. And basically it says, if your system's been well maintained, sort of like the oil fields in Ramallah, right? Most activities that you do, and there's a table for the activity based on the voltage level and so on and so forth, which basically tells you, yes or no, you do need a PPE, you don't need a PPE. But the problem with this is that the informational note is not a part of the code. It's basically for your reference. It's sort of give you sort of an idea what the intent was, right? So the natural inclination of most of us has been up to this point is that we put together the systems and we put the worst case arc flash label on that piece of switchgear. Now, the other aspect and the trade-off of that, of course, is that more PPE is not necessarily better. I mean, if you read 1584, IEEE standard 1584, which most of these calcs are based on, what it basically tells you is that what you have to, another one of those trade-offs, right? Because what happens is, as you start getting into more and more protection, the PPE levels goes higher and higher up, you start limiting the mobility of the individual doing the work. You start having visual range of acuity, being able to see peripherally gets kind of difficult. And a lot of the mundane tasks that you do manually on a switchgear or the piece of electrical equipment starts getting incredibly difficult to do in these protective environments. So more PPE is not necessarily the best answer. Just basically don't say, hey, PPE 4 everywhere, you can't do anything unless you're in PPE 4. Just, that's not a valid solution either. Okay. So let's step back for a second. So what do we do when we're doing analysis for our environments? For us, and you'll see this in a little bit, we've been using the arc flash analyzer, report analyzer feature of ETAP quite a bit. That was a godsend for us. One of the major reasons we started using ETAP, quite frankly, was the ability to create multiple configurations and multiple scenarios and be able to model those all in a reasonable fashion. ETAP is a very good software package and application platform for that sort of analysis. So what we used to do, we create all the multiple scenarios. 1584 basically tells you need to have all the configurations, the minimum fault, the maximum fault. That's another misconception, by the way. How many times have you done a study and somebody has called you up and said, hey, I have two identical panel boards or switchboards, they're literally right side by side. One is a PPE 4, the other one's a PPE 3 or 2. How can that be possible, right? Same thing. So the point is that we have to create all these scenarios. Minimum fault current, maximum fault current, which is, if your systems are simple and they're radial, it's not that big of an issue. When your system is a data center such as this one, how many multiple configurations do we have? What you're looking at here is an actual data center that's been constructed. It's a tier 3 data center. By the way, the difference between tier 3 and tier 4, the concurrently maintainable versus fault tolerant, this topology is fault tolerant, but we didn't go for tier 4 just because of the fact tier 4 also has some physical separation and barriers and protection requirements, uptime requires, which we didn't feel they were warranted. But if you're looking at this system, we have two primary medium voltage feeds. We basically have medium voltage distribution with a tiebreaker and tie between them. We have unit substations. Essentially, each unit substation can be fed from either medium voltage distribution side, either utility source. Each unit substation has its own dedicated generator. This is basically a block redundant topology. Then, to make matters more interesting, each one of these is, by the way, is a UPS system and critical distribution, each of these 5 primary distribution systems here. Then we have what we call a maintenance bypass and load bank substation. Basically, the purpose of which is to be able to take any generator, any UPS, and essentially load bank it individually from a single common load bank. And at the same time, what you're going to see in the next slide is that we can actually then put the critical load, because we don't want to take it down, remember? We can put the critical load on generator bypass, and we can load bank the unit substation that was normally feeding it all through a series of loops and basically bus configurations, which you can barely tell or make out here. So how many configurations is that? 2 utilities. You can operate from either side. Each utility, each critical substation has basically a maintenance bypass, a wraparound bypass, and a maintenance bypass station, substation feed. It can add up rather quickly. And basically, we would sit there and we would try to model these things. This particular one, what we did was we ended up settling for 13 configurations and scenarios on this one, because some of them, and that's the point of this exercise, I guess, some of them are more common, and there's really not much reason to model them. So this is what I was talking about here. So what you can see here is this is the UPS system serving the critical load. This right here, this side of the isolation breaker, this is the load bank loop. You can bypass the critical load, which is down here, either through this direction, or this is a bypass feed here as well, which allows you to use the same substation, this maintenance bypass substation, to either feed the load through its generator, bypassing any given generator, any UPS. We can basically reconfigure this data center and feed everything any which way but loose. Okay. A film reference which nobody in this room is probably going to get because it's way before their time. So what would we do? We would run this, we would do the analysis, and then we would basically put the worst case fault current, the worst case incident energy. It would go on a label, and that's what we would put on the piece of switchgear or multiple sections of the switchgear. This is where we started looking at this, and we started looking at the notion that, back when I was doing coordination studies, and we basically were doing it by hand, and we were basically using onion skin and the old see-through curves and so forth, and trying to do this, you were not going to do a bunch of scenarios and different alternatives, right? But with the advent of software like STAR, and you can basically go in there and you can just create the scenarios, create the configurations, and go nuts with it, right? What I always tell the younger engineers when they're coming up is just because you can do something doesn't necessarily mean you should, right? There's just a point of diminishing returns. So that kind of goes to this too. What we started looking at was that, yeah, there are all these different configurations, and we can basically identify a configuration that might actually be the worst case incident energy in a particular portion of the distribution. The problem is that particular configuration or that particular sort of state of the system may not necessarily make sense in terms of the activity that you're going to perform at that substation. So the point being is the label is supposed to be there for standard or normal operations, right? When you're doing something, it gives you a baseline protection level. It's the last line of defense, right? What you're really supposed to do is put yourself in a electrically safe working environment, but more importantly, you have to have a work order. If you're doing work on an energized substation or an energized electrical system, you're supposed to create a work order, a method of procedure, MOP, to basically do it. So our position has changed. What we basically have decided to do, what we've started doing is that we don't anymore just go ahead and put all these configurations together and then basically print out the worst case particular incident energy label for that piece of switchgear. What we do now is we basically look at the configurations, identify, and working with the owner and the operator in particular, come up with the most likely sort of configurations where they would be expected to do, for instance, switching operations, maintenance operations, what makes sense. And we essentially put that particular configuration on the labeling and on the switchgear. The thought process being is that anybody that's going to do work in that particular portion of the system, an essential part of the work order for them to be able to do that work has to be for them to identify what state they're going to put that that piece of the gear or that portion of the system into, and identify that as part of the work order, and suit up and do their PPE accordingly. Not necessarily just rely on what's on the gear. That's a minimum. That basically makes sense in a certain level. If you have a radial system, with 2 sources and maybe 3, okay, yeah, you can do this. But with a system like that I just went through, a lot of the configurations that you're going to try or you can put together that are possible are not going to be necessarily the ones that are going to make the most sense for somebody to be working on the gear. So that was it for me.